Hamiltonian quantization as Rocek algebra. Thank you very much for the invitation. It's great to be here, and it's a special honor to talk about quantization from the Hamiltonian perspective in an institute named after Galileo, because I'll try to emphasize the usefulness of separating kinematics and dynamics. And I think Galileo sort of invented kinematics. And one reason is that he didn't have the full power of calculus to use to solve differential equations. He could solve basic equations that didn't require more technology. And so, nevertheless, he was able to say a lot of things by studying kinematics. And so this is the approach that I will try to advocate, that if one wants to work out all the mathematical details coming into quantization, then the standard approach is to solve the equations of motions first, and then write out the fields explicitly, and then quantize the modes. But in general, this can be hard. It can be hard to find explicit solutions to the equations of motion. But nevertheless, if one takes a Hamiltonian approach, then you can still compare kinematics and formally dynamics by seeing what happens to given Hamiltonians, for example, under certain symmetries of the theory. So I'll also, since I will talk about vertex algebras and quasi-vertex algebras, I'll build upon the previous series of lectures by Raimundo Pirulani. I'll recall some details, but refer you to his online lectures for more information on the proofs. So let me start by recalling some of the ideas. So first, let's look at the picture. This is sort of basic construction, but is the essence of everything that is going on. So one starts with a Lie algebra, plain Lie algebra. And then one can take its universal enveloping algebra, and this is a so this is the universal enveloping algebra. And this is an associative filtered algebra. And where the filtering is given by the degree of these non-commutative polynomials in a given basis is chosen for the Lie algebra. So this is degree less than I, and it's generated as an associative algebra by F1, the first piece of the filtration. Then from here, one can take the associative gradient with respect to the filtration, and one gets the associative gradient of this universal enveloping algebra, which comes with a Poisson bracket, which is the associative gradient shadow of the commutator, which is canonically associated to an associative algebra. So this can also be written as the symmetric algebra over G. with its Poisson bracket, or equivalently can be thought of as a function of the dual of the Lie algebra, again, with bracket. And this is a graded Poisson algebra generated in degree 0 and 1. And then, if I take just the degree 1 part of this graded algebra, then I essentially recover my original Lie algebra back. So remark, more generally, one can start with an associative filter algebra and take the associated graded. I'm assuming the filtration is nice enough with respect to the product. Take the associated graded and then you get the graded Poisson algebra generated in degree 0 and 1. And this can also be thought equivalently as a Lie algebra or a Lie Reinhardt algebra. So Lie algebroid is a Lie algebra object in the subcategory of sheets, and the Reinhardt algebra is basically, if I start with P graded, I have a ring which is P0, and then this acts on P1, and also P1 acts on P0 by derivations, and P1 acts on itself by the bracket, and this data satisfy the suitable compatibility conditions. And now one can go back from the Poisson objects to the associative object by quantizing. For example, using Kontsevich procedure. So let's look at one basic example. So I can take X, possibly super manifold, and then I can associate with its tangent sheaf. So this is a Lie algebra in the category of OX modules of sheaves over X. And now I can repeat this construction in this particular case, and then get this the symmetric. So this is a tensor category, so I can consider form of polynomials in this object, and this is nothing but the Poisson algebra of functions over the cotangent bundle of X with its standard Poisson structure. And in this case, I can do canonical quantization. So this procedure here is explicit, and all I can just treat this as the algebra object and construct its universal enveloping algebra, which is nothing but the sheaf of differential operators, which acts on the sheaf of functions in the usual way. So I can think this sheaf of functions here as being the space of states in some sense. Right. And so notice that here I'm allowed to work with sheets because I can always choose a nice filtration of my associative algebra of the modules, where the filtration is given by the degree in the fiber direction of the cotangent bundle, and so it's insensitive to what happens on the bases, so I can localize over the base, and of course, if I had chosen a different filtration, for example, the Bernstein filtration, that wouldn't work. So it's not necessarily the best filtration in more cases, but it always works in a uniform way that allows them to sheetify.
What it doesn't do is give an answer that only depends on t star x. In other words, if t star x is also t star y for some other y, you won't have a natural relation between these two definitions.
Yes, that's true. So there will be cases later on like this that I would like to address. That's right. But it's other than that, it follows the procedure that I outlined for the algebra objects. So this works more or less for any the algebra object in any reasonable category. So you can work with the super manifolds. Any times you have a nice tensor category, you can do something like this. However, there is one case where it is worth spelling out separately, and is that of the conformal algebras. Because in that case, the tensor structure is kind of unusual. So I have the conformal algebra. So this is the algebra in the category of differential modules, but with the weird tensor structure. So the bracket is given like this, where this is a map of k d1, d2 modules. So I have this is a KD module, this is a KD module, so this the tensor product. Here the wedges for saying that this is symmetric is has a natural structure of KD1, D2 module, and this is G tensor with KD1, D2 over as a KD module. So this is the right version of the bracket. It's called the lambda bracket in this category of KD modules. And it turns out that one can similarly construct a conformal version of the universal enveloping algebra, but now instead of an algebra, it's the structure that the result had is that of vertex algebra. Which is the conformal algebra together with a sort of associative product and a filtration, and it comes to the filtration. For the details of what the particular construction, I'll refer you to Raimundo's notes. But this is essentially the idea, and then I can take the associated grade object with respect to this filtration, and I obtain the analog of what I had before, and now instead of
could you tell some, because people were not
For,
here
for
about
purpose-
this, just basic things to
Yes,
people who were not here 1 month ago.
right, so you have,
Not all.
so essentially it's supposed to be, to record the product is supposed to be the product of fields. So it has a lambda part, because this is in particular a conformal algebra. It has a lambda bracket that is encoding the singular part of the OP, and then you have the normally ordered product, which is the extra structure that you are adding to this conformal algebra to make it an associative algebra that has to satisfy certain analogs of the associativity and commutativity of the algebra, but corrected by some lambda terms that depends on.
But if we weren't there, can we think of it as just an algebra of holomorphic fields under operator products?
Yes, in a sense, yes. Yes.
The K of D is just a way of saying that you're allowed to take the derivative of a field, I imagine.
Yes. So this is the D is basically counting how infinitesimally far you are from the diagonal, or in more concrete terms, it's counting how many derivatives of delta functions you have. And this is the lambda that appears here.
I think this is Katz's invention. So if you take the normal formalism for P with normal ordering, what Katz invented, let's do Fourier transform. So he introduces a formal parameter lambda, which is bookkeeping device for keeping delta functions and derivatives of delta functions. So
Right. So you can write formally the. So you have something like, say, sigma lambda x sigma prime. So you can think it of as the formal Fourier transform of the actual commutator. And so this is going to depend on sigma prime, and then integrate over the sigma. So you get something that is a polynomial that is lambda, so you get some transformation rules that can be worked out.
Will it be important for your lecture to do that for you?
No, not really. So the examples that I give are actually rather trivial in the sense they can be all worked out explicitly. But I just mentioning this because I think it might help somebody to see conceptually where this comes from. Is thinking of this as an analog of the previous construct of the universal enveloping algebra. And okay, so
Actually, I do have one more question.
sure.
What you mean by the universal enveloping algebra for the vertex algebra, do you consider multi-level products? Or do you consider only local polynomials and X and its derivatives?
So they
A typical object is going to be a polynomial of X and its derivatives, or evaluated at one point, or they're evaluated at different points.
so you have so when you iterate the products or the bracket, you can have different type of singularities taken into account. So the relation is sigma goes to sigma prime, and sigma prime goes to sigma double prime, and so on. I don't know if this is what you mean by multilocal.
No, just ask additively, what is U of G? For ignoring the products. If G has a basis of things like X of sigma,
yes.
and then do we consider X of sigma becomes X of sigma prime? Or do we only consider X of sigma
X, so the, right, so the thing is that once we pass to this compound tensor structure, we don't actually have sigma and sigma prime anymore. This is, I'm just going to have one, say, I don't know, I have the Virasoro, in field notation is written like this. The commutator, I would write it as something like this, right? So I don't actually have the explicit appearance of the coordinates. It's possible to go back and write the usual vertex algebra axioms by explicitly writing out the state field correspondence and showing that once you know the lambda bracket and the normally ordered product, then you can recover the usual field definition. And so this is a usual vertex algebra. But in this, when I think it as an object in this compound category, then I don't have any actual variables up here.
I think there is a confusion since you didn't give a definition of lambda bracket nobody knows.
Yes, sorry.
But it's basically one has to think it's Fourier transform. So once you transform, you get.
What did you transform?
So
Forget not worrying about the way it's packaged, but are we actually discussing operator products of local operators?
Right, we're discussing this, but what is important is keep track of singular parts, right? And,
so it's a vertex algebra. So all operators are assumed to be mutually local, in the sense that their OP contains only finitely many derivatives of the delta function. All right, so then the corresponding notion of Poisson algebra is Poisson vertex algebra. Again, generated in degree 0, 1 in this particular case. So this is the analog of Poisson algebra in this compound category, where this weird tensor product. And then one can recover G by taking the degree 1 part just to be. And more generally, this picture now it's going to look like this. So, well, generally we have now filtered vertex algebras generated in degree 0 and 1. That's right, by the first positive term in the filtration, and to this by taking the associate gradient, I get Poisson vertex algebras. Generated in degree 0 and 1. And this is equivalent data to having a Courant-Dorfman algebra. or almost equivalent in my think about the degeneracy of the inner product, a current algebra. And then again, one can ask whether one can quantize and go back. If I start with the Poisson vertex algebra, can I get a honest vertex algebra out of it, so that I can go back and get the same thing that I studied. So two examples. One that is sort of intermediate between the standard big picture that I presented at the beginning and this compound version. We start with a Lie algebra. With some invariant symmetric form. One can construct out of it a conformal Lie algebra, the algebra of currents of G, where the bracket is given by the old bracket plus lambda times the symmetric form. And so this now is a conformal Lie algebra, where this Lie bracket is taking into account the structure of K modules, of differential modules. And then I can write down its universal about algebra, that's the coordinates. And I can take the associated gradient and get the Poisson vertex algebra. And so forth. Okay, so this sort of intermediate example. And this is the vertex algebra associated to this Lie algebra. Another example, to erase. Is that of the standard current algebra associated to the manifold. With respect to the manifold, I can associate to it the current Dorfman algebra associated to Tx and Tx star. Algebra in the category of OX modules, where the bracket is the usual current bracket and the inner product is the tautological product on T plus T star. Okay, so out of it you get an object here, and now we would like to know what is the right quantization in this picture. And it turns out that the right answer is, well, it turns out that if you try to do it naively, you cannot always do it. There are some topological abstraction that you have on X for these two work. But there is something else you can do. You can write Y as the odd cotangent bundle of X. And this comes with a projection to X, that's any bundle. And now you can write the pullback of Tx plus Tx star. And notice that you can write it like this as the odd tangent bundle of Y. Y is the supermanifold. And well, and this is falling back into the first type of examples that we look at. It's just a rim of Lie algebras. And so I can construct the algebra of function over here as I take in the symmetry tensor powers of the shifted tangent bundle of y as an OY model. And then quantize just as before. And then, so this is something that is a sheaf on y, and now you can push it forward and get a sheaf on x, which is essentially what one called the Caillard sheaf on x.
One question. This identification of the shifted tangent of y with this pullback, it depends on the choice of the connection to the diagram.
Oh,
It's not natural. Because you need to split into the tangent to the base and tangent to the phi.
yes, I think you're right. Yes. Yes. Yeah. Right. So there are many choices and many ways to write the tangent bundle to the supermagnitude for sorts of identification. So you can think this as a quantization of the cotangent bundle to this supermanifold, or the tangent bundle of this supermanifold. And as such, it acts on functions over the base. And then using the various isomorphisms, which way we think of what is the dual of what, by taking a couple of double duals, you can also think of this that it acts on functions over the odd tangent bundle of x, which you can identify with differential forms on x. This. And this contains inside those differential forms of degree less or equal than 1. It's the equivalent of the first term of the filtration, F1, that we had before. And now this forms of degree less or equal to 1, you can think it in a sense as being functions, as functions on the loop space. Functions on the loop space of x, thought as the space of max from S1 to x, because if I have a 1 form, for example, I can construct a function that evaluates on the loop. This is just the integration of the form over the loop. So one can think of this as a formal quantization of the loop space of x, because it fits in the same picture that I had at the beginning of the board. You have some space of functions over some object, and then an algebra of a Lie algebra object that acts on it, and you can think of this as a quantization, because it came from the same type of constructions before, taking the universal logarithmic algebra of some cotangent bundle. So now this raises some question. So to what extent can we we think of this as quantization of the cotangent bundle of the loop space of X, quantization in the sense that I said before, we have a Poisson algebra, Poisson object of functions in here, and you want to find some associative object that in some limit recovers what you have. And second, how is this related to quantization of the sigma model with target on X. So a priori there's no immediate connection with the sigma model, just quantizing the cotangent bundle of the loop space, and one needs to make this connection.
So when you say quantization of the sigma model, can I think of it as a standard path into quantization?
No, that's the next remark. Yeah. So natural connection of question 1 to question 2 is through Hamiltonian composition. So first, what do we mean by this? So first we endow this. First of all, we think the cotangent bundle of the loop space as kinematic data of loops moving in the target X. And we endow it with Poisson data so this could be an actual Poisson structure or maybe a Poisson vertex algebra structure. But what I mean by Poisson data, it means an identification of the algebra of classical observables, which is some subset of functions on the loop space. So this functions on the cotangent bundle of the loop space. It's an identification with infinitesimal symmetries of this algebra. Right, so what does Poisson bracket do? Is allow me to think of functions as derivation of the algebra of functions that I'm looking in, so infinitesimal symmetries. So this is what I mean by Poisson data. So you can mean Poisson vertex algebras, Poisson algebras, or something even more general. But I would like to think this as part of the kinematic picture. And then there is the second step is the quantization. And By quantization here, at this stage, I mean just the kinematics. So find some associative data. Again, it can be one is the associative algebra or a vertex algebra or whatever general group that is one is looking at in the particular case. But what we want is that it somehow indexes on a maximal isotropic space of classical observable, and we want to be able to recover our Poisson data as some kind of limit. For example, if we have a filtration, take the associated gradient with respect to that filtration. And finally, as last step, distinct from this kinematic quantization, add dynamics by choosing a particular observable as Hamilton. That is going to describe the time evolution as in the usual way, using Hamilton's equation. Okay, so this is the most natural thing to hope, using this prescription as what we get as quantization of the loop space, and perhaps this can be interpreted as a quantization of the sigma model. So it will be a Hamiltonian picture, as I said in the beginning, this has the nice feature that if you have two models that you would like to describe as equivalent, maybe related by some kind of equality, then you can at least check the equivalence at the purely kinematic level, and then say that you can, under this duality, you can map a given Hamiltonian that you have on one side to a Hamiltonian on the other side, and this way realize the equivalence of the two models without having to write down, without having to actually solve the equations of motion. And this can be an advantage in some situations. Any question? Yes.
About the sigma model.
Yes.
You're thinking particularly of a cylinder as a worksheet, or it is?
Yes.
And no other case?
Yes. In this formalism, one mostly looks at the cylinder.
At the cylinder.
So of course there are many other and more powerful ways to do quantization of the sigma model, for example, using Feynman integrals and things like that. But if one wants to have some really concrete mathematical objects to work with, this is one way of doing it. So you get actual modes and you can test.
But what physicists understand as the sigma model doesn't actually lead to something as concrete as this. My understanding is that you have to consider what people sometimes call the 0-2 model, and then you take the cohomology of one of the supercharges, and you get this kind of story.
Yes, that's one way that is one can think of how the chiral-Gram sheaf enters this picture of quantization as relation to this model. This is one way, but in that picture, that picture starts already with the Lagrangian formulation of the 0-2 model. So
well, actually, 2-2 if you want to get chiral-Gram. 0-2 leads to what people call chiral differential operators.
Right, so you want to look at the holomorphic sector inside the 2-2 model, and certainly that's that's great that one can do that, but I would say that from a mathematician perspective, it's still a little bit unsatisfactory because one cannot get an isomorphism on the nose of two algebraic objects, for example, and call that
it might be unsatisfactory, but it is how what you're talking about is related to what physicists do.
No, absolutely.
Whereas what physicists call the sigma model, per se, is much more complicated.
Yes, and so in these lectures I'll try to address some things that one can, so I'm not claiming that this is the ultimate answer of what the quantization of the sigma model should be, but what I'm going to try to argue is that one can see lots of features that one would like to know about the sigma model already in this framework. And to a mathematician like me, this has the appeal that I can prove everything rigorously and get nice isomorphism structures in the nodes. But I understand that
I think chiral-Gram complex it's a trick to build operator algebras, right? And then you can think, look from, that chiral-Gram complex has it from Lagrangian or Hamiltonian point of view. I think you're advocating more Lagrangian, and he's trying to say that chiral-Gram complex, it's Hamiltonian, you can look at Hamiltonian.
Whether it's Lagrangian or Hamiltonian, if you want to ask how it's related to standard construction by physicists.
Well, but I can tell you how this guy started to work. So Helloani, as a mathematician, tried to construct a global sections of 2,2. Algebra as a mathematician had no clue about sigma model, and then he just realized that in his construction he gets a Hamiltonian, and that Hamiltonian is sigma model. That was an accident. That's why
It does not contradict what I said about.
No, but I'm saying there are two different points of view. There is no contradiction.
Absolutely. And what I like about this picture, maybe physicists can appreciate it, even though it's not as useful for their purposes, is that this is the direct generalization of the usual Hamiltonian quantization of the cotangent bundle of a manifold. So I think, if nothing else, it has this aesthetical appeal. That if one believed that quantum mechanics was the right thing to do, then this is the right analog in the loop space version. I'm not claiming that it solves any problem that the physicists might have. At least not that I'm able to say it, but maybe somebody can push it further. All right, so let me point out one example, and then I'll continue next time. So, example. So from this point of view, of writing down explicitly everything and checking that one gets quantization and isomorphism of dual models, this has been worked out by Kapustin and Orlov in all mathematical details and nuisances, by myself and Helloani from a different point of view, that I try to allude to, and more recently by Malikov and the Shetland. So in the Lagrangian approach, to make the connection in the Lagrangian story, so this model is simple enough that I can actually go back and forth with the Lagrangian Hamiltonian circle. One looks at fields as maps from a cylinder into the target, in this case the torus. These are my coordinates, and then one writes down the usual Lagrangian. And say the Euclidean signature. As a two form, they can integrate, and then one solves, let me emphasize this, one solves the Euler-Lagrange equation of motions, and you get Laplace equation. And then you can construct your KD module in the language that I alluded to at the beginning by looking at the space of solutions of the equations of motion. So you can think this as a jet space of the space of maps from the cylinder to X that satisfies the Euler-Lagrange equations. And concretely, since this model is so simple, I can write it explicitly as the mapping space, which I'm going to write as the function of the space is function on S1 cross R cross X. I get the graph of the given map as defining the delta object inside the space of function distribution, and then I act by derivative with respect to tau and sigma, and then quotient by the ideal generated by the operator that is defined by the Lagrange equation. Okay, and now I can restrict to the time t tau equals to 0, and what we get is now time was r, so that goes away, that is 1 cross r equals x, and then I can write all derivatives with respect to tau thanks to this equation in terms of derivatives with respect to sigma, except for the first one, which I'm gonna keep here. So this is sigma, this is xi, and here I have d by d tau xi. And now this is, and then I have all the action of all the sigma derivatives that are left acting on this. So this is a k d by d sigma model in the language that I was developing before. Or equivalently, you can think of this as the jet space of functions from the circle to the cotangent model of x. You can identify this as the cotangent direction of x. Okay, so now since I have maps with the domain on S1, the jet space is just given by taking derivatives with respect to the sigma direction. Okay, and then so this is a K model, it fits the picture as before, and you have the bracket that makes it into a conformal Lie algebra. Is like J is given by lambda delta ij. Alright, and now you get out of this a Poisson-Vertex algebra, which is the chiral on X. So you get the Poisson Vertex algebra that is the chiral on this torus. Notice that here I didn't have to pass to super manifolds or anything, because my manifold is parallelizable and everything works fine just by looking at the zonic part of the ring. When should I stop?
You start with 5 more minutes.
Okay.
4 minutes.
Yeah, well, that is correct. I can stop at any time. Just, you know, it's, I don't know when we start. All right. So notice that here we have a problem because so this construction doesn't see the winding sectors of the model, so no windings. And there is no way it could, because this is a shift, so it localizes on X on the target space and doesn't know anything about long loops that can stretch across the manifold. So this is an instance when the target space is not simply connected, that kind of ramp sees something but not everything. So it cannot be the final answer. And well, okay, how to add windings? So there are 2 ways. So one way is to look at the spectrum of the operator. So one ties this vertex algebra, that's commutators, and so you like to look at the spectrum of this operator, integrated along this one, and you see that this is Zn, the lattice that we use here to take the quotient. I'm going to call it lambda, and similarly, if you integrate the t, you get lambda dual. And then one passes to complex coordinates by writing z as square root of -1 sigma plus t. And then in these coordinates, one has that the spectrum of I dz of x, the joint spectrum is minus I d bar x. This is given by 1/2 using the off-disjoint coordinate, 1/2 lambda plus lambda dual with lambda and lambda dual in lambda plus lambda dual. Okay? And then you have your Hilbert space, the space of states on which, so first you get the Fock space, which is functions on the modes of dz, and its complex conjugate.
What are we thinking X, capital X to be in this discussion?
Oh, sorry. Capital X was the n-dimensional torus. Then the complex conjugate, and then these are Heisenberg algebras, conformal the algebras. And then finally, you write your Hilbert space as the sum over all these possible eigenvalues of the induced representation of the trivial representation of the Fock space of the positive modes, lambda minus lambda dual, tensor, the induced representation of the complex conjugate guy. Okay, so this is the one-dimensional representation which the positive, the non-negative parts x, or the positive parts are trickier than the zero part x by eigenvalues. And then you construct in the usual way, so we'll just keep the construction, we don't have time, and you already know it anyway, of the Virasoro and the complex conjugate of the Virasoro field. And then you want to extract the chiral part out of this. And so the vertex algebra is given by taking so those vectors in the Hilbert space that commute in the sense of the lambda bracket with the antichoromorphic Virasoro. And it turns out that this is just the chiral graph if lambda is not equal to lambda dual, that is the self-dual radius. I haven't introduced metric here, but if you want to identify lambda with lambda dual, you have to put a metric. So this is chiral, so you see no windings, but on the other hand, if I am the self-dual radius, then this is what one expects. So it's the sum of over lambda in just one of the two lattices of the first. Actually, so lambda is equal to minus lambda dual. So equal to minus lambda dual, and so this is just C lambda. Okay, so this is what is also known as the lattice vertex algebra. So it's an enhanced version of the chiral that takes in account the windings. Okay, so
if I understand correctly, the previous construction was for any x, except that sinc x was a complex manifold.
Right, so for any x you can get this shift, this chiral shift that in some sense you can think of the compensation of the kinematic of the cotangent boundary of the loop space. But here in this particular example, I can work out the details, so it's very simple, and I get this answer.
But that's right, but it's not the details of the same thing. Now you actually are studying what physicists call the sigma law. And then you're looking at all the homomorphic operators in the sigma law.
That's right, because this time, in this particular derivation, I started with the right lambda Lagrangian and then solving the equations of motions because they were particularly simple, and this is the answer I got. So what I plan for the rest of this lecture, but I will do it next time, is a purely Newtonian approach that tells you that you can get the same thing back. So I'll do it tomorrow. I'll stop here.
More questions?